Hello, good afternoon, everybody. Thank you very much for this opportunity. And thank you very much for all the audience attending today's conference. And I hope you enjoy this virtual and possibly a hybrid conference. Unfortunately, I'm not able to come to the conference in person. Let me start the PowerPoint presentation. Let me share screen from now. Share the screen. And there is a presentation here. Oh, I have to swap the screen here. Okay, great. So my talk today is about the cost-effective integration of second life EV batteries with solar PV systems for commercial buildings. And today's talk will include a few things here. So I'll start by looking at, let you know where I am from. And then I'll look at the overview of second life EV battery for building energy storage applications, in particular where there's a solar system installed. And then I'll talk about the aging of second life EV batteries, how to get the data for that second life use, and how to predict the life in their second life use. And then I will let you know what we did with the two pilot test sites facilities in San Diego, California, in the United States. And then we'll discuss about optimizations that we are planning to do with the energy storage systems. And finally, some observations and takeaways from our study, and also showcase some of the other activities at SDSU. Well, first of all, I am from San Diego State University, which is located in San Diego, which is the southwest corner of the United States in California, close to the Mexican border. The university is roughly 50 miles from the downtown of San Diego. And if you walk into the San Diego campus, and you will have a really good feeling about the architecture, the campus, the beautiful campus, and which has 125 years old of history. So since 2020, a few months after the pandemic started, we received this project from the California Energy Commission to study second life EV batteries when they are paired with a solar system in a commercial building. So as you can see here, what we're developing is a storage system for a commercial building where there's already solar panel installed. So on the left hand of the slide, you can see that on the top, there is a solar panel installed on the solar roof building, and then there are connectors, which are the solar inverters connected to the solar system, and they are connected to the middle, the AC bus. Towards the bottom left, you can see that there is a metering for the building, and then there's a usage for the building. So all the energy from the solar would go through the AC bus to the building. That's what exists already now. On the top, of course, the AC bus is connected to a transformer, which is from utilities. What we're doing is on the right hand, where you can see at the bottom, we already developed this SCADA controller and the data hub, which is used to control the storage system. About the computer, you can see there are different batteries. In our application, in our study, we can use any battery packs, any battery modules in combination. And each battery module is connected to a battery inverter, which may also include DC-DC converter between the battery and the inverter. And in other combinations, we also have the batteries connected in parallel with a DC-DC converter. Below each battery pack, you can see there's a BMS. The reason is that we need to know the condition of the battery, so we need to have a BMS. Now, of course, this BMS can be either from the battery pack or it can be external. In fact, later on, I will discuss about this, because when you use a battery pack from a vehicle, then there's an issue with multiple battery packs connected in parallel, because all the BMS are going to share the same ID when they send information to the CAN bus. So what we need to do is to design a gateway which is used to receive information from the vehicle BMS, which is still inside the battery pack, and then translate that information into a different message, and then use that message to connect to the SCADA data hub. Over here, we actually use a model bus to communicate all the data messages. Now each gateway is going to send a message with a different ID. For example, the cell voltage, the pack voltage, the cell current, SOC, things like that. So this is the overall configuration of our energy storage system. Importantly, there are different battery packs, and there's going to be gateway. There's going to be a central controller. That controller actually conducts a lot of functions, and we'll discuss later. So in order to understand how long these batteries will be lasting inside energy storage system, and what kind of battery that can be used for energy storage, and how you can manage them in that energy storage system so that it can provide you with the best return on your investment. So we started with the battery aging study. We started the study by selecting 4 different kind of batteries. Of course, there's many kinds of different batteries for different manufacturers of vehicles, different battery manufacturers, different chemistry, different size, and so on. So we selected these 4 batteries because of their availability, and also because their availability due to the aging of the vehicles they have been in the market. For example, the Nissan Leaf Case 1 is focused on Nissan Leaf Gen 1 battery. These batteries are at 24 kilowatt hour. These are lithium manganese batteries. They were in the market since 2012 until 2020 for 8 years of service already. So we tested about 100 packs. We found each of the battery is roughly at 60 to 70% of their state of health. In case 2, we look at another kind of battery, which is a newer battery used by Nissan Leaf. They're at 62 kilowatt hour. This is a lithium nickel manganese cobalt kind of battery. This battery is relatively new, so starting in 2018 to 2020, only 2 years old. We got about 20 packs, 24 packs of this battery. Now you might ask, this battery is fairly new. How do you get this battery? Well, this battery is in fact mostly from warranty. And also some of the batteries were never installed into vehicles because they were marred, which means they have minor damage before they put on the vehicle, things like that. So we tested about 20 of them, and we think that they qualify for second life EV battery because these batteries cannot be used by EVs anyway. And if you just have put them in some sort of application, now this is a perfect application for those batteries. A third category is kind of a non-road vehicle, not on-road vehicles. In particular, this is from electric forklift. We tested 3 battery cells, and they started at 89 SOH. With the pack level, however, is only 50%, and I'll explain why. Because the batteries are heavily unbalanced. The balance system inside the battery pack with the BMS itself didn't work very well. So after 4 years of service, these batteries are aged quite quickly because of cell imbalance. The pack is at 50%, but individual cells at 89% from our testing. These are lithium iron phosphate batteries. Case 4 is a battery pack from electric buses, and this battery is also lithium iron phosphate. They're rated much higher at 270 mAh. They also retired roughly 4 years in service, and we tested those batteries again, similar to the forklift, because they are both lithium iron phosphate batteries. Those battery packs at 52% only SOH, but the cell level, they're actually at 75%. So you can see balance is critically important for lithium iron phosphate batteries. By the way, the packs from Nissan Leaf, both Gen 1 and Gen 2 have pretty good balancing performance in their batteries. So once we got those battery packs, this example of Nissan Leaf Gen 1 battery. So we started to do the pack level testing to understand how these packs would perform after they are removed from the vehicles. The Gen 1 batteries are mostly in the vehicle for 8 to 10 years already. So in this setup, we have a very simple system. So we have a DC power supply to supply power to the battery. Then we have a electronic load to consume the energy from the battery pack so we can simulate the discharge. And we have a gateway to read the BMS information from the vehicle BMS so that we can understand what the cell voltage and other battery parameters. And also we have this space where we use it to design a real-time controller so that we can do the testing automatically without a human intervention for the process. So this is the whole battery pack testing system we developed in our laboratory for the second life UV batteries. And if you look at the battery packs that we tested, this is on the top bottom left corner. We tested about 100 batteries, and we found that these batteries are anywhere from 60 to 67% SOH. And then these batteries are probably running from 2,000 to 3,000 cycles already in the vehicle life. Therefore, these batteries are pretty much okay for energy storage application because they still have 60 or more, 60% or more for energy left inside the pack. So looking at the pack testing, and you can see that we have some of the data displayed here. We perform discharge and charge, and we look at the capacity. For example, this pack has 70% of capacity left, and we look at the cell voltage of each cell inside the pack, and we look at the impedance and so on. And we found that this cell capacity is pretty consistent. There are no serious balance issues with the battery packs. So after that, we disassembled the battery pack. We got the cells and the Gen 1 battery. So each cell is pretty good sealed inside the mechanical shell. So since we estimate they already had 2,400 cycles, 8 years of service, which means it's about 14.6% degradation per 1,000 cycles in vehicle applications. But we know that in second life storage applications, we can control the environment, and also we can control the charge and discharge rate to be much more moderated than it is in a vehicle application. So we predict it will last much longer in second life applications. So on the right hand, the top graph shows the testing we did inside the laboratory for 2 battery cells, the C1, C2. As you can see that those batteries degrade pretty linearly from the beginning of our test until roughly 3,500 cycles. As you can see, the drop is SOH drop is roughly 3.6% for one cell and then 3.9% for another cell per 1,000 cycles. So this is much less than the degradation in their first life application, which is roughly 14.6%. The internal impedance, including R1 and R0 and R1, they both increase, relatively increasing, but not at very fast speed. And in fact, this data a little bit old. In the last month, we have found that at some point, this impedance will increase dramatically, and the capacity also increased dramatically, which means they're going to reach the new point. At that point, I think this batteries should be good enough to retire. Some data to show different groups, and we tested 24 battery cells for the Nissan Leaf Gen 2 batteries. And as you can see, the aging is very interesting. It's aging quite fast in the beginning, and it's slower afterwards. And as I mentioned earlier, after roughly certain number of cycles, they start to show the aging need of those batteries. The aging speed is roughly 3.6% per 1,000 cycles for many of the batteries, but we did show that the 1C and 100 DoD is bad for the battery aging, but 0.5C and 80% DoD is very good for the battery. So this is how we, let's see, sorry. So demonstrations, I'm sorry. I ran through quite a few slides here. So this is Gen 2. And for the lithium iron phosphate batteries aging testing of the forklift, these are the lithium iron phosphate batteries. As you can see, the top graph, the aging is pretty consistent. It's roughly linear. It's a little faster in the beginning, but slower afterwards. We tested two kinds of batteries in this category. The top one has a very good capacity when we got them, and then the bottom two has a little bit lower capacity when we got them. So we did the testing. As you can see, they're pretty consistent. You can actually move the top line to connect the second line quite easily to understand the whole aging of the battery. So they're aging roughly 4 to 5% per 1,000 cycle, which is good. The impedance, it's also interesting to see the impedance at the beginning is higher, but after like 1,000 cycles, the impedance start to decrease and pretty consistent so far. So we think that those batteries are quite good. And then for the electrical bus batteries, we found that there are a lot of inconsistency in the battery. So therefore, it is very hard to use the batteries at the module level, pack level. So we would have to either disassemble them to use them at the cell level, or we have to find a way to balance them. So we have not done a lot of research in these batteries, but this graph just shows when we do the characterization test, how much SOH they are inside the batteries. So the conclusion is that the Nissan Leaf 1 battery, even though they are used for a long time in vehicles, so they have a relatively low SOH, like 64%, they're still good for second life use for about at least 10, 12 years. For the Nissan Leaf Gen 2 batteries, because they're relatively short in their first life, and they are good for maybe even 20 plus years in second life use. The electrical forklift, also good for 20 plus years in their second life. And then the electrical bus has a balance issues, and we didn't move on with the testing because of limited ability in our laboratory. The electrical forklift, of course, even though they're good for 20 years, but they also have balance issues. So you either have to disassemble the battery to use them at the cell level, regroup them, or you have to find a way to balance the battery inside the module or inside the pack. So with that aging study, we're confident that we want to install 2 pilot testing sites. And these 2 pilot testing sites are all located in San Diego. And we estimate the cost for deployment at each facility. On the left hand, we estimate it's going to be roughly $96,000. It's a 22,000 square feet building, roughly 2,200 square meters. We estimate the lifetime savings of the system will be $300,000, and the solar generates 180 kilowatts. The storage is going to be 220 kilowatt hour to 380 kilowatt hour, and this is going to be deployed in the next couple of months. Another building is interesting. It's a smaller building, has a solar panel. The cost is relatively smaller because we're using only 2 battery packs at 120 some kilowatt hour. The cost $86,000. It's only going to save $200 per month, so it's not going to recover the investment in about 10 years, even longer. It won't recover because you're only going to save roughly like $2,000 to $3,000 per year. So it takes much longer. So it's not going to recover. However, the reason we do this is because the owner have told us that they can use this battery, and it is designed for resiliency, which means if there's power outage, they can use battery pack to power the building for at least 1 to 3 days for critical loads. So therefore, they're going to save money over there because each energy interruption for 24 hours, they're going to lose 50 to 100K. So this is interesting scenario for the second storage application. In order to deploy the application, we need, as I mentioned earlier, we need to design a gateway. The reason is that the battery pack they all have a BMS inside, but the BMS sending out the signals with the same CAN ID. So therefore, when we put them on the same CAN bus, they're going to be confused. We're not going to be able to identify which parameter belongs to which battery pack. So therefore, we design a gateway. So this gateway is connected to the BMS on one end, and then with another CAN, this BMS has 3 CANs altogether. Another CAN is connected to our data center to connect the data. And it also has a CAN to connect to our computer so that we can control the system like relays, things like that. So this has been done in the laboratory, and we're ready to deploy them in a field application. To design the system, we apparently have to pay attention to a couple of things. For example, we need to contain them inside a container so that they don't experience rain and other weather conditions. But when we put inside a container, we have to deal with the thermal and also structure, like to make sure they are safe inside the container. So our idea to purchase shipping container, and we're going to paint the outside to look nice, and inside we put the battery pack and all the electronics like the inverters, the DC-DC converters, and so on. And we simulated the thermal performance, and we think there is air conditioner to be installed so that they can maintain a relatively lower temperature during the summertime, because inside the container it can be quite hot in the summertime. But we're going to put the insulation inside the container so that the air conditioner will have a much better thermal performance. We also have to design structure to hold the battery, so we can put the batteries like on top of each other on a structure. This structure has to be able to hold the batteries. Each battery is roughly 1,100 pounds, 500 kilograms, quite heavy. And also they have to sustain a certain level of earthquake performance, like in San Diego. That's something we have to be careful. And also we design the structure to hold on to either the base or the side of the container to hold the power electronics devices inside the containers. And as I mentioned, in order to connect those batteries to the AC grid, we do need a DC to AC inverter. So we we were planning to design our inverter, but we thought it would be much better if we purchase commercially available inverter for site demonstration, because this inverters are going to be used for the next 10-20 years. We tested those inverters with our battery, and we implemented our control like the grid time mode, active reactive power control, grid forming, islanding, and so on. So we make sure they work. And if we use many battery packs, it is possible that some of the battery packs are going to have lower SOH than other battery packs. So the ideal condition, we need to connect the DC-DC converter between the battery and the inverter so that we can control each battery pack independently, whether it's a charge, discharge, or balancing, so we can make sure the whole battery system, the energy storage system, can work consistently for the same amount of time, so that you don't have to swap out the battery pack in the middle of the application. So this is very important. So we also purchased this DC converter, and this DC-DC converter has been tested, controlled, but there are some issues and now they are being repaired. So we're working on that one as well. So the next thing is that we need to control the whole system. You can imagine that we need to understand the battery condition. We need to make sure the batteries are safe. We need to make sure the battery aging consistently. That's from the battery side. On the other hand, we want to make sure that we will be able to control the usage of the system so that we can take advantage. I mean, the purpose of the storage system has 3. One is that we want to make sure it can help the building to cut off their peak use so that they pay less money in the demand charge, and even this wow compensation. And secondly, we want to make sure that these batteries can shift their use from peak charge hours, peak read hours, to super off-peak hours, what it means that we can charge the battery during the solar generation, or we can charge the battery when the price of electricity is low at night, so we can use it during the peak time, during the peak demand, hours. When the rates are high, we can use the energy from the battery so that you can cut down the demand charge. You can cut down the peak use charge. And the third function is to make sure it can form an island operation during the power outage so that you can use the battery energy to supply electricity to the building. So those are the three functions. To realize that function, we need to design the controller. We call this modular energy management system, or MEMS. So that MEMS will be able to protect the battery, control the battery, do the local analysis, do the system monitoring, and do the model predictive control. Since a lot of functions embedded in this EMS. And that EMS diagram, basically, it takes the usage data of the building and do the model prediction, and do the forecaster, and then you do the model predictive control to realize the functions I described earlier, and then to save the building owner money by cutting down the demand charge, the peak use charge, and to do the backup power. In the meantime, it will do the balancing, the power distribution between battery packs so that the batteries are aging quite reasonably in the same fashion. And also, it's going to make sure the system is safe. And if there's any issue, they will report so that we can do maintenance of those battery packs. The MEMS design is done that we have the software, we have the hardware related to the whole system, so we are ready to deploy this. And this system are developed based on software like MATLAB, and of course, eventually it can be standalone once the system is deployed. I mentioned about island operations, so this is an important function for energy storage system because you want to make sure the system can help the building to supply backup power. And we tested operation of the system and it also works. I mentioned about the balancing. The reason you need balancing is because when you put up a system, we really don't want to replace one of the battery packs in the middle. We want to have them consistently age in the process. So therefore, if we find one battery pack has less SOH than another one, we probably use less of that battery. Or if we find one battery has less SOC, we want to balance that SOC. So we do this control through the MEMS system. And this is the example how we do the balancing based on the control system and so on. So this is, what we do for the, I mentioned about the demand charge and the peak use charge. One important aspect is to be able to predict the usage of the building. And the usage of the building can be predicted based on the historic use, like each day, each hour of each week. And also based on the solar condition. If you have the weather forecast data, then you can predict how much solar can be generated, right? So if, for example, if we predict it's going to be rainy tomorrow all day, so there's minimal generation, next day, we should be able to charge the battery at night using the grid electricity once superly low rates, and during the next day, during the peak use, we'll be able to use that electricity to cut off the peak charge, right? If we predict there's a huge summer generation, solar generation coming up, so we should pre-empty the battery, not empty, but make sure the SOC is at the point that you can charge the battery from the solar so that you don't waste the solar, because sending solar energy back to the grid will not make you a lot of money. It's better to store them inside the battery. So those are the forecasting models, and then we do the model predictive control to make sure that we have this owner to save money. For example, in this building, based on our simulation, the average savings is about $250. For the peak, we save about $740. And of course, it really all depends on the size of the building, the size of the solar system, and the electrical usage. Some of the buildings are able, for example, one site, we predict they can save roughly $3,000 per month and $300 over the lifetime of the system. So this is quite different based on the buildings. The peak shifting is quite an important aspect of the energy storage system. As I mentioned many times, we charge the battery at low rates and then we discharge the battery at high rates. So therefore, the money can be saved. In this example, for the ideal situation, the regular charge is 308, and then demand charge 632, and the total charge is $1,200, the red one, with the ideal condition. Of course, in real life, there's always variation in the usage of the building, in the weather forecast, nothing's accurate, precise, so that the savings will always be less. That's why if you look at without MPC, the total charge is $2,564. With method 1 is $2,200, method 3 $23, and method 5 is $2,100. Ideal situation will be $1,200. So our goal is to reach as much as we can to the ideal situation. And we also design algorithms to extend the life of the battery systems. Basically, we are proposing, for example, to do the different charge rates based on the aging study, not 100% duty. We maintain the duty at 80%, and also we maintain the discharge rate at a lower rate, for example, 0.5C or less. Therefore, you can be sure that the system can have a longer service life. Now, of course, you might question, is that 0.5C reasonable? Because in vehicle applications, you often design the battery to be 4C, even 8C, or even higher. Well, that is true. In vehicle applications, the storage pack, the battery pack is typically relatively small. But in building energy storage applications, the storage pack is the overall system is typically much higher. Well, how higher? That would depend on the size of the building, the electric use, the solar systems, and how much investment that can be recovered over time, and how fast we can recover the investment. So we will design, we're in the process of design this battery energy storage system size optimization. So based on this program, we will be able to look at the data from the building, existing data, and resize the system so that you will be able to recover the cost with the best investment. So this is very important for the application. So now let me summarize the talk, which are takeaways from these observations. Now, since that I did not talk, that I want to summarize here. First of all, EV batteries still have a residual value when they are not good for EV applications, whether it's range, or whether acceleration or performance. So they can be good for energy storage applications. When combined with the solar system, it's important. Without solar, it will work, but it was not as good as if you have a solar system. The energy storage system can help reduce demand charge and peak discharge, and also provide electricity backup during a power outage. The second life battery are cheaper than new battery, so they're good. They are a good option. It probably last for 10 or even 20 years, depending on system design. Now, however, there are issues that I didn't mention in this limited time talk, is that logistic related to battery removal from the vehicle, storage of the battery, testing those battery, transport those battery to a place where it's being used. It's quite difficult, and it's something that has to be addressed sooner than later. Batteries can have health conditions and imbalance of cells, and how to deal with those situations can be quite difficult. If you want to disassemble the batteries for use, that's going to be quite challenging, because that's going to increase labor cost, which might make it more expensive than new batteries. And designing the container and the structure to hold the batteries can be quite difficult, because different batteries come with different shapes, different size, and so on. So those can be difficult. And then the next one is reliability and also liability. And if there's something happens, who is responsible for the liability, whether it's the EV manufacturer, or whether it's the installer, or whether it's the system developer or the building owner themselves. So who is going to certify those battery systems? So some of these questions are still there. Now this has to be resolved. And finally, I just want to demonstrate a few other things that we do. So in addition to the second life battery, our team have been working on battery management systems for a long time, and we have developed our battery management system, hardware, software, algorithms, SOH, SOC, things like that. So these are some of the things that we do. Another project, we were heavily focused on for the past 10 years was wireless charging of electric vehicles and other applications. And the wireless charging, as many of you have some advantages, and they're probably going to become an option and be available for different applications, for different customers and different OEMs. Of course, we're still in the process of addressing interoperability, installation issues, and maybe even economic issues, things like that. And then the last project I want to demonstrate is that we're working on this flying cars, electric airplanes. And as we know, aviation emits a lot of CO2s that they contribute to the global warming, global climate change. And one of the things that people have been studying in the past couple of years is to move also airplanes to be electrical. Our study is focused on a electrical vertical takeoff and landing airplane for about 4 passengers, maybe 1,000 pounds of cargo, and with a distance roughly maybe 150 miles range. So this is not full-blown passenger vehicle or cargo vehicle, but this is more for emergency application, for medical emergency, for like disaster relief, things like that, because it can take off and land vertically. So the usage will be very universal. We also have published a number of books, and we have developed different type of vehicles, things like that. If you have further interest or questions, please visit our website for the information. And finally, I want to acknowledge the California Energy Commission for their sponsorship in this Second Life EV battery study. With that, I want to conclude my talk. I will thank you again for your attention, and please contact me if you have any questions. Thank you very much. And my contact information is on this slide. Thank you, and bye-bye.